The first step to solving this problem is to read it and find out what it's asking you. Ultimately, we are going to find out how many of these molecules are polar. We are given 5 molecules, and we'll do some steps in order to figure out what is polar. So a basic overview of what is going to happen is this. We have 4 molecules. We're going to draw the Lewis structure for each molecule. We're going to find the formal charges, find the partial charges, draw the dipoles for the bonds, and find the net molecular dipole. Something to note right off the bat is that if we end up having a net molecular dipole, the molecule is polar. If there's no net molecular dipole, the molecule is nonpolar. Next, we're going to do the Lewis structures for each molecule. First, let's look at SO3. The valence electrons in sulfur is 6. The valence electrons for oxygen is also 6. However, there is 3 oxygens, so that will be 18 valence electrons, having a total of 24 valence electrons in our Lewis structure. Sulfur is the least electronegative, so it will be in the center of this Lewis structure. First, you're going to connect the sulfur to the 3 oxygens, and then you're going to fill the outer oxygens until you reach 24 electrons. Something to note about SO3 is that there are 3 Lewis structures. This will result in a resonance hybrid, creating a 1 1/3 bond between every oxygen. These are your Lewis structures for all 5 molecules. Next, we'll be looking at formal charges, partial charges, and determine the bond dipoles. So first, let's look at oxygen F2. In order to find the formal charge, we're going to do oxygen, 6 valence electrons minus 4 non-bonding electrons minus 2 bonds. That is going to give us a 0 formal charge. Then we have F. F has 7 valence electrons, 6 non-bonding electrons, and 1 bond, giving us a formal charge of 0. An important thing to note when doing formal charges, you want to make sure that the more electronegative atom has a negative formal charge and not a positive formal charge. And this is for if the formal charge is not 0. Ideally, you would want 0 formal charges for every atom. To find the partial charges, we'll be looking at electronegativity. So let's look at oxygen's electronegativity and fluorine's. One thing to note is that the more electronegative atom will have the partial negative charge. The least electronegative atom will have the partial positive charge. If you look at the periodic table or your notes, you'll notice that oxygen has a smaller electronegativity than fluorine. This will give oxygen the partial positive charge and the fluorine the partial negative charge. Here are the partial charges for each molecule. Now let's look at bond dipoles. Bond dipoles are indicated by an arrow with a tail and a head. The tail of the arrow will be at the partial positive atom, and the head of the arrow will be going towards the partial negative atom. This arrow shows the flow of electrons. Let's look at the bond dipoles for SO3. The tail of the dipoles all start at the partial positive sulfur atom, and they will head towards each oxygen atom because it is partial negative. Just like you can see in this one, oxygen has the partial positive charge, so the tail end will be at oxygen, and the heads of the arrows will be going towards the partial negative fluorine. Here are the rest of the bond dipoles. Notice that for ozone, it's going to be nonpolar because no bond dipoles are denoted. Now let's do molecular dipoles. There's arguably two ways to do this. The first way is to draw a picture of all the bond dipoles. You would see if the dipoles cancel each other out, making it nonpolar, or if they do not, they add together, making it polar. The second way is to use domain and molecular geometry to determine if it's polar or nonpolar, which we learned in class and is also in our notes. Let's look at SO3. On the central atom, sulfur, there's 3 domains. There are 3 bonding and 0 non-bonding on sulfur. This would make the molecular geometry trigonal planar. This trigonal planar molecule will have angles of 120 degrees. The bond dipoles will cancel each other out, having no net dipole, and SO3 is nonpolar. Now, let's look at this molecule. Oxygen, the central atom, has 4 domains, 2 bonding and 2 non-bonding. This has a molecular geometry of bent. Now let's go over here and look at this. These are the bond dipoles at the top. This at the bottom is the net dipole. OF2 is polar because there is a net molecular dipole. If we look at the other 3 molecules given, we'll notice that all 3 of them are nonpolar because all of them give us no net molecular dipole. Here is an overview of the bond dipoles and molecular dipoles that were formed from these molecules. Notice that only OF2 has a molecular dipole and is polar. So the answer to our question is 1. 1 polar molecule out of the 5, OF2. Now let's do a recap and show some common mistakes that may happen. Looking at the overview of our procedure, we can see, did we do all these steps? Did we find all these things in order to find our answer? Which is true, we did. The first thing we did was draw our Lewis structures, then we found formal charges, then partial charges, found the dipoles, and then found the molecular dipoles. A common mistake made is that BE violates the octet rule, and that's okay. BE only wants 2 bonds, and it will only have 2 bonds in this Lewis structure. You do not make a double bond between the BE and Cl. You will leave it how it is because BE is an octet violator. Another common mistake made with Lewis structures is the order in which to fill the electrons. First, you will connect all the atoms together with 2 electrons. Then, the remaining electrons will be placed on the outside atoms. If any remain, fill them on the central atom. But you must make sure that atoms have 8 electrons and follow the octet rule unless it is a known octet violator. Atoms with a high electronegativity will draw electrons to them. So, if an atom such as oxygen or fluorine has a positive formal charge, this does not go well. It's important to remember that atoms with a negative formal charge should have a higher electronegativity. High electronegative atoms do not want a positive formal charge. Another common mistake is made with bond dipoles. Bond dipoles will start at the atom with the partial positive and go to the atom with the partial negative. The head of the arrow will be facing towards the atom with the partial negative charge. This atom will receive more electrons because it has a higher electronegativity and wants more electrons.